Good afternoon, everyone. My name is Liz Tran. I'm the Community Relations Specialist here at CUAHSI. I would like to welcome you all to the 2017 CUAHSI Cyberseminar series on hillslope hydrology and earth system models. Just want to point out that there is a Q&A. This is a very lively discussion. So after the presentations, we will have people ask questions and join in the discussion, and we ask that you connect via phone for better audio connection. And so the slide is up right now for you to dial in if you are based in the United States. If you're located outside the United States, we ask that you connect via VoIP, but make sure that you adjust your settings so that if we do decide to unmute you, that we don't receive feedback on the call. Lastly, if you have any questions or comments, please send a message to the questions chat box or raise your hand, and we will unmute you from there. And I'll pass it off to Ying.
Thank you, Liz. Can you see my screen now?
No, we cannot see your screen yet.
Oops, I think there is a screen, show my screen. Okay, I need to push this button. Can you see now?
Yes, we can.
Okay. All right, I'm going to start with this slide again, like last time. For those of you who weren't with us last time, and first of all, thank you for coming. Welcome. Good morning, good afternoon. And so again, I wanted to give everybody a little bit of context of this webinar series. And this is a NSF-Inspire project funded by Hydrology and the Climate Large-Scale Dynamics Program, and to improve the hydrology in Earth system models. And this slide pretty much I stole from Leo, and pretty much sums up our problem. And I draw your attention to the bottom two boxes. And in the lower right box is a land model grid on the order of at least 1 degree by 1 degree, which is about 100 kilometer by 100 kilometer. And there are indeed subsurface heterogeneity, and there's some misconception here. It's not entirely uniform. For example, in this chart, it's shown that the land surface is divided by many, many tiles, and primarily by land use and land cover types. And in the natural vegetation part, we have a dozen plant functional types. But what is missing from a hydrologic perspective is the terrain features, the variation within the box, the hills, the valleys, and shown in the left. And so Leho's figure brought out two terrain features. One is the elevation difference. And there are ridges in the valleys, and then there are sunny slopes and shady slopes. And these differentiations within a large model grid can create patches of heterogeneity and a structure in water and energy balance. And so this is an example of the kind of hydrologic common sense that we hydrologists know very well, and this is scale we work on. We have lots of ideas how to represent this in Earth system models. So that's the goal. And we organized 5 webinar series to explore these issues. And on the bottom of it, I wanted to draw your attention to the goal. What is the end product? What do we deliver at the end of this exercise? Hopefully, we can write up a community synthesis paper. This is the second paper under the Inspire project. The first one, Martin Clark led, gave us really the scientific motivation to do this and some broad blueprints how to do this. And now we're going to get into the nitty-gritty details and really sort of lay out what we know and what can be done immediately right now and how to do it right. And what are the additional global analysis that we must perform before we really know how to do this. And so hopefully this document will be useful, and everybody is invited to contribute toward this document, and which is the purpose of this synthesis activity. And so last Friday, we had our first webinar asking this question: where in the world is hillslope hydrology important to ET and photosynthesis over a large ESM model grid? And we had 2 presentations, which basically opened up the discussion and gave us some starting point for the discussion. And our goal there is to come up with a global framework to look at the global picture where hillslope is really going to make a difference. And today we're going to move on to our second seminar, asking the question: what are the basic subgrid units? How do we divide a large ESM model grid into meaningful units, hydrologically meaningful units? And how does water move through these units, and how are they connected to surface water features? And as last seminar, we're going to start with the 2 short presentations from Pieter and Xubin and Hoori. And the structure will be the similar as last time. We'll let Pieter talk, and after he finishes, we will answer a few questions that really pertaining to Pieter's talk and hold the bigger questions until after Hoori's talk. And then Hoori will give her talk, and we'll do the same thing. So with that, I want to pass this to Pieter.
Okay. Share my screen. So do you now see my screen?
Yes.
We do see your screen.
Okay, wonderful. Well, good afternoon, everybody. My name is Pieter Hazenberg. Welcome here from the University of Arizona, where it right now is actually quite cold, the lower 80s, but still very pleasant, of course, as always. And so today I will discuss some of the things that we have been developing here over the last couple of years to represent our hill slopes in Earth system models, or more specifically within land surface models. And let's see whether I can go to my next slide. There we go. So as Zeng already indicated in the introductory slide, and also during last week's talk, we're focusing right now, if we look at the current generation of land surface models, they're focusing more or less about a ½ degree or a 1 degree scale. And at this scale, many subsurface processes, our subgrid processes, are taken into account. And the example here is specifically for CLM 4.5. However, if we move down towards the hydrology of, in this case, these type of land surface models, and it's pretty similar between most models. First of all, if we look at some of the key deficiencies that are in the hydrology of large-scale models, is many of the current generation of global land surface models make use of a constant depth to bedrock. So the so-called more or less is constant across the globe, which of course we know from hydrology is definitely not the case. And just to let you know, we've developed over the past couple of years, more specifically John Pelletier developed a method to estimate global depth to bedrock variations. And we assume that that will soon be implemented across the globe. And that data set you will present in 2 weeks from now, when we're talking about generating data sets for global land surface models. Furthermore, if we focus on the hydrology that is currently available, the subsurface hydrology or the groundwater response, the base flow right now is represented in many models by this relatively simple top model based equation, where groundwater flow is a function of some kind of a maximum groundwater flow that is exponentially decreasing as the depth of the groundwater table from the surface increases. And next to that, at the ½ degree or the 1 degree scale, there right now is no horizontal movement of water through the subsurface. And as such, all the runoff, of course, takes place only through the river network towards the ocean. And on top of that, which is very important for arid areas, there's only one-way interaction between the river network and the subsurface below, where only the subsurface is losing water, while it cannot gain, the rivers cannot lose water towards the subsurface. So what we have been developed, and that's all fine, of course, when you're looking at the model of a ½ degree or a 1 degree resolution, which is given here in the image on the left, where the left panels indicate the elevation that we derive from a digital elevation model, and the right images, the right panel defines the depth to bedrock. And if we move, of course, from a 50-kilometer resolution towards a 10, towards a 5, towards a 1-kilometer resolution, well, we see, of course, first of all, that there's much more small-scale variation in the landscape. And at these smaller and smaller scales, it is, of course, known that the importance of lateral flow becomes more and more important. Furthermore, of course, elevation variations, small-scale elevation variation increases over smaller when we move towards higher resolutions, indicating the importance of hill slope flow. Plus, on top of that, at the very high resolution, we of course see a more explicit representation of the stream network, and as such, the interaction between the stream network and the hydrological subsurface below, of course, increases as well. So what we have been doing is we've been developing a so-called a representation to define small-scale flow within land surface models, with the idea that currently there's already a lot of knowledge available, a lot of detailed process representation available in Earth system models. So can we somehow make use of what's already available and somehow add the smaller scale lateral flow representation? And we would like to do that in such a way that we first of all incorporate as much cross-discipline knowledge. So that's why our team covers both hydrology, geomorphology, as well as atmospheric sciences. We prefer to make use of constrained physics-based parameters, which of course I know is a sensitive topic in hydrology. What's a physics-based parameter? But what we mean here more is we would like to be able to estimate as many parameters as possible from large-scale available data sets, and of course focus on a scale small enough that would enable comparison with in situ observations. Now, of course, the overall dilemma here is that how do you develop a scheme that is, on top of that, also computationally efficient? So what we've been developing is a model that we call the hybrid 3D hydrological model. And so what we have been doing, first of all, we took a step back, basically going back to our Hydrology 101 class, where we know here in the panel A in the lower left side of this figure, we know that the hydrological response in a hilly environment is, of course, governed by, first of all, the first order hill slopes, the higher order hill slopes, the riparian zone, and the interaction of the riparian zone and the hill slopes with the channel network or the stream network. Now, of course, we can never represent each individual hill slope within a large-scale land surface model. So, for instance, within a land surface model with a resolution of about 5 square kilometer pixel resolution. So instead, what we have been doing, we've trying to conceptualize this highly detailed system using the representation that is given on the lower left, where we on the one hand define, in this case, 2 representative hill slopes, a representative hill slope that is representative for the first order hill slopes, which are generally assumed to be convergent and flow into the headwater streams. The higher order hill slopes that are generally interacting with the riparian zones, and of course in the middle there's a riparian zone that is interacting with the river network. Now, of course, we are aware that in every 5 square kilometer pixel, there might be a different distribution of hill slopes and riparian zones. So if we move up towards the highest elevations in the Rocky Mountains, it's probably 99% hill slope and only 1% riparian zone. Well, if we move below, if we move towards the delta area, in this case, we would have 100% riparian zone or 100% what we call plain, and there would not be any hill slopes, while there will still be the interaction between the river network and the riparian zone. And so to speed up runtime performance, runtime speed, a main step that we have been, on which we have been focusing on, is separately solving vertical from lateral flow. And one of the reasons why we want to do that is because right now vertical flow is already represented in these large-scale models. And so why reinvent the wheel again and just make use of what's available there right now and add the lateral flow scheme? And the benefit of that is that speeds up computational performance. As I mentioned, we explicitly represent the differentiate between hill slopes and plains. And as you see here from the bottom below from the image on the bottom left, we extend the soil column, or in this case, towards the bedrock, or more from a hydrological perspective, we are focusing on the unconfined aquifer up towards the first aqueduct. Now, so to explain a little bit more of our approach, so here on the left picture we have, let's say, the standard vertical column that is now represented in any major land surface model, which we describe vertical flow by Richard's equation, and we see that extra term R, which already right now is given in these models, which is basically the root extraction rate. What we want to add to couple the vertical response with the lateral response, we'd like to add an extra term G, which similar to the root update, basically represents the lateral flow through the saturated zone. So in this case, G is positive or negative and when we're focusing on the saturated zone, so everything below the groundwater table in the image on the left, well, G becomes 0, so there is no lateral flow for the unsaturated zone layers in the soil column above. So, and then we can couple such a soil column with basically any type of lateral component. So in this case, if we focus here on the hill slope component, which is given here in the upper figure on the left, we represent the hill slope component. As I said before, we represent either groundwater flow, lateral groundwater flow through the hill slope, or lateral overland flow. And so lateral groundwater flow, how we represent it, we make use of the hill slope storage Buzynski equation, which is given here on the middle of the page. And we see that that hill slope Buzynski equation, storage Buzynski equation, has a recharge rate, in this case R sub. R sub, we can estimate, that's basically the recharge rate from the groundwater table that we estimate from the vertical column solution, and that then drives lateral groundwater flow at the hill slope scale. Similar thing we do as well for the overland flow, where we solve the diffusive wave equations in a similar way to obtain the lateral flow at the top of the hill slope. Now, as I already mentioned, as already shown here in the top left figure, we basically, as I said before, we basically represent a given hill slope by its characteristic shape. And here at the bottom, I have given just 3 characteristic shapes: a typical uniform hill slope, a convergent one representative for the first order hill slope generally, and a divergent hill slope representative for the more higher order hill slopes. Now we've implemented this system for a number of situations. In this case, we have implemented the system where we have one vertical column, so vertical column that is coupled with the saturated zone, which is presented in the top left figure, and then in the top left figure on the right panel, in this case panel C. We've also implemented that with a single vertical column that is connected to each lateral node of the saturated solution. And we've compared our model results on the one hand with a solution that is now implemented within the community land model, which we call one column CLM, which is the results are given on the left. And we compared as well our results with a model called CUAHSI, which is a explicit 3D Richard solution model, where we for now assume that the 3D Richard solution model is our best estimate of the flow processes through the hill slope. And so what we observe, first of all, if we compare our 1 column or our 20 column results with the 3D Richard solution CUAHSI, is based on the soil moisture that we observe in the soil column. We see a much better resemblance between our situation with the 3D Richard model. And if we compare that as well with the situation, the way it's being described right now in the community land model, we see as well that the current representation is quite off. Another benefit, which I don't present here, but you just have to assume for now, is we did a runtime comparison. And the benefit of disconnecting the vertical and the lateral flow and couple it efficiently but don't solve a full 3D Richards equation, that saves us in computation time about 2 to 3 orders of magnitude, which is a main benefit, of course. Now, of course, this was just a theoretical experiment. We've also tested our model, at least for the Hillslope scale, in this case within the Biosphere 2. The Biosphere 2 is an indoor unit here in close to Tucson, Arizona, where we have 2 hillslopes available, a Leo hillslope, which is a convergent hillslope, and a mini Leo hillslope, which is a plain hillslope. And here the image on the right shows the results. On the one hand, the black line shows the observed values. The gray dots show our model, the hybrid 3D model at the hillslope scale. And the dashed one shows the result, again, of the 3D Richards model, CUAHSI. And we see that both if we look at storage dynamics in panel B, the base flow response as well as the overland flow response, you see that our model does a very good job in representing the flow within Biosphere 2. Now, of course, Biosphere 2 is still an idealistic hill slope, but it's much closer to reality than just a numerical experiment. Also here at the bottom on the left, we see for the mini Leo hill slope, for another experiment, we compare our models, volumetric water content and matrix potential estimates to those that are observed. And we see that our model captures the observed values rather well. Now, of course, this is just at the hillslope scale. We've extended, we're currently extending this model to full catchment domains using 2 different approaches. On the one hand, in the top figure, we have still the situation where there's interaction between the stream network and the riparian zone. But then by identifying only one representative hillslope, which is releasing its water both to the river network as well as the subsurface of the riparian zone, or the plain in this case, or the situation that I described before, where we have a given first-order hillslope releasing its water into the river network directly, and a higher-order hillslope that is releasing its water into the groundwater system of the plain. Now, at the regional scale, so if I move beyond one individual pixel, what we assume is that lateral flow through the groundwater is represented by simulating, in this case, a 2D Darcy model only for the plain section between different grid cells, as well as through the river network. Well, the river network and the plains and the riparian zones are effectively interacting with each other, so allowing for two-way interaction between the stream network as well as the subsurface below. And we've, so I guess that's what I identify here, like the interaction between the stream network and the system below is what we do there. We couple that explicitly or implicitly, we couple that together, which basically results so far from what we've seen in an efficient solution. Furthermore, we go beyond, let's say, the classical mod flow based approach, where the channel network is represented by a classical rectangular shape. Instead, we make that shape flexible to efficiently also allow for overland, over bank flow in this case, while still being able to interact with the subsurface below. Now, we are testing this model right now, both for MOPEX as well as for a small basin in the Amazon. And the image on the right just shows some first order results of our model with respect to observations. All the colors give results for different parameters, and the black line shows the observed. And of course, even though there are differences, we do see that the signal that is observed from the observations looks like it's first order being well captured by the model. Now, of course, this is just a first order result, and we're still testing this to go within MOPEX, this work is still in preparation, which I hope to submit for reviews in the coming months. And that was all from my side. So, as I said before, we represent hill slopes as well as the riparian zones. I'm aware that our approach looks like it needs a lot of parameter information about the subsurface. My colleague John Pelletier will actually show some of the geomorphological possibilities that are out there to actually represent those parameters and to estimate those parameters from large-scale land surface models, large-scale digital elevation models and geological data sets. That was it. Thank you.
If anyone has any questions, please type it into the chat box and we'll unmute you, or just raise your hand.
Can I ask a question? This is Ying. Peter,
Sure.
Do you envision this way of breaking the landscape into these upland slopes, first order slopes, or lower order, higher order slopes that drain into the riparian zone and the riparian zone itself? Do you think this way would work almost everywhere in the world? Or is the geomorphic structure? I mean, you are, the studies, I can see the way you do it work well in many of the topographically, high relief terrain, right? You can really define the stream network. And in some parts, like what we discussed the last webinar, obviously when you have strong topographic relief and then hill slopes are the fundamental units, right? And this is the work and shown early on, in the 60s, 90s, 60s and 70s. And if you look at Tom Dunn's earliest work, and he measured those slopes and runoff coming out of those slopes from different depths. And what his data has shown, the three convergent, divergent, and uniform slopes behave very, very differently. So I totally get that. I think this is a great way of dividing up the landscape. So my question is more like, what about the rest of the world when you don't have such a well-defined fluvial system? Have you thought about those?
So the way we've, I will be honest, our representation is very much differentiating between the uplands and the lowlands, and assuming that, let's say, the identification of hill slopes is representative for the uplands. Well, for the lowlands, the way we've defined it so far within our model is just saying in the lowlands there are no hill slopes. And as such, the effective area of the plains, which the plains in the uplands is the riparian zone, and in the lowlands, let's call it a delta area or something like that. That effective fraction of the plain increases and towards the total size of a given grid cell, whether that's 1 kilometer or 5 kilometer. So then, for lower elevation, the behavior of hill slope or the impact of hill slopes is not taken into account in that case. So we have John created at the global scale for each 1 kilometer the total fraction of hill slopes within a given pixel. As well as for the hill slopes, what a representative first and higher order hill slope shape is. And so if I'm in a lowland system, and then the fraction of hill slopes is 0, and as such the flow behavior of hill slopes is not taken into account.
Okay, we'll hear more from John in the fourth webinar. Okay.
We do have one question from Zeng, so I'm going to unmute you, and you can ask your question. Zeng?
Yeah, my microphone is not good.
Okay, I can just read your question then, and then Peter can answer it. So his question is considering microtopography example small elevation variation of land surface needed, or is it commonly negligible?
That's a very interesting question, actually. So what our approach was, let's say at the sub-kilometer scale, or if we focus on the 5 kilometer grid cell, any scale that we go below is basically the differentiation between hill slopes and plains. But then beyond that, microtopography is something that right now we don't take into account. I'm aware of that it's there, and I think it's very important. What I'm afraid of if we start adding that as well is that we're really demanding a lot from our computational performance. So no, in that sense, it's not taken directly into account in this approach. I hope I answered your question properly, or at least sufficiently for you.
Any more questions before we move on to the next presentation?
I think there's a question from Steve Burgess.
Yeah, I think it was more of a comment, but I will unmute
Okay.
him. Steve, you're unmuted.
Can you hear me?
Hello?
Yes.
We can hear you a little bit, yeah.
Okay. I think I just summarized it very simply in the issue that the whole problem is characterizing the subsurface and its hydrogeologic properties. That's been the killer forever. And there's nothing that's in here that's really getting us to address that issue. And I have no idea how to take Richard's equation over the spatial domain to cover that. Did you get that?
Yeah, no, I absolutely agree that the subsurface is still an issue here. And so I might not have explained it properly here, but I agree that conductivity variations at the subsurface is something we haven't covered yet. The step forward I think that we have made already is that we've developed it's a first order approach, but at least it's applicable at the global scale, is to get estimates what's the, let's say, the size of the unconfined layer, the depth of that. And that, of course, is a first step forward in the sense that it constrains basically our lateral hydrological flow domain. Instead of making use of a classical only a transmissive peak value only, that a lot of people have exponentially decreased with that. We said, okay, let's at least make it more explicit and differentiate on the one hand between two locations. There's a difference in depth to the first aquithird or depth of the unconfined layer, and then once we've solved that, and maybe then the next step would be is to start focusing on how do you account for variations in conductivity and how that affects my 2D RC solution or my Hillslope storage Boussinesq equation solution, which I agree with you is far from perfect, but it's the way at least how I see it is a step forward from where we are today or where we were 5-10 years ago. And so I see it more as an ongoing challenge, and this more as a step in the right direction. But it is not the final answer. I absolutely agree with you.
Well, in the interest of time, let's hold other questions. Let's have Hoori talk first.
Hello, good afternoon, everyone. Can you hear me?
Yes.
Hi, thank you for the opportunity. Today I'm going to present the work that I did as part of my research when I was in Australia with Ashish Sharma and in collaboration with the Bureau of Meteorology on developing a new semi-distributed hydrologic modeling approach for soil moisture and runoff simulation. And our goal is on watershed simulations at larger scale and be able to develop a system that is computationally efficient, so it allows us to do uncertainty quantification and be able to run lots of model simulations. And the focus is on how actually we achieve this by discretizing the catchments to our different units. But how it fits with the ESM scenarios when we have these larger scale atmospheric grid cells, we think that perhaps we need to delineate the landscape to, our watershed units and then start looking at hillslope processes. So the objective of this work was to develop a computationally efficient hydrologic modeling framework for soil moisture and runoff simulations. And to do that, we had to define computational elements in a way that they represent hillslope hydrologic processes and be developed in a way that these hydrologic response units be topologically connected, so at least capturing that water moves from upland to the lowland areas and somehow capture the spatial heterogeneity of landscape that impacts water balance and energy balance partitioning. To do that, we developed this smart modeling framework, which is written in MATLAB, and we start the catchment discretization by using a digital elevation model. We delineate our subbasins using the TODEM toolbox, and then within each subbasins, we are delineate the hillslope units. And finally, we go and use topographic and geomorphic analysis to delineate hydrologic response units or landforms that maintain this topologic connectivity, which I go through much details. Now it comes to the model simulations. We have multiple approaches that you can do simulations within each subbasins, either discretize a subbasin to the series of cross sections and do 2D model simulations, or make further simplification, essentially integrate the properties of these cross sections to representative hillslopes, or what we call them as equivalent cross sections. So essentially, instead of simulating 20 cross sections across the subbasins, we are only simulating 3 equivalent cross sections using 4 hydrologic response units that are topologically connected. So that's where the computational efficiency comes into play. And in this case, we are using a 2D unsaturated zone hydrologic model based on Richard's equation. But the nice thing about this framework is that you can plug in any hydrologic model that you want. The main idea is the way that we are breaking the catchments to these computational units. To do this semi-distributed modeling with a SMART, we first need to do catchment scale topographic and geomorphic analysis to delineate our hydrologic response units. After that, we either do distributed cross-section modeling or equivalent cross-sections. We perform model simulations. In this case, I'm using MATLAB parallel processing toolbox, so we can simulate multiple cross sections at the same time on high performance machines, so we can speed up our calculations and then finally post-process our modeling results. Here is how, again, the frameworks look like, and I'm going to go step by step how we are doing this discretization in more detail. As I mentioned, the routines all are written in MATLAB. I've written series of custom functions for the hillslope delineations, and essentially there are 13 steps involved to doing hydrologic modeling, from the delineation up to the production of soil moisture distribution and runoff within a catchment. So we start with the topographic and geomorphic analysis. We get the DEM, delineate our first order subbasins, delineate hillslopes, and now landforms or our hydrologic response units. And to show the examples of these landform delineation, I'm going to use a data set from a catchment in Australia, the Hoori River catchment, and I'm going to discuss how we delineate these landforms in particular. And the idea is we are using, in this case, average slope for every pixel in the catchment versus distance from the river to delineate these types of curves. And we identify the thresholds within these curves, which is a breakdown in the landscape. So in this case, we are discretizing the hill slope to 4 units: upper slope, mid slope, fit slope, and alluvial flats. And the nice thing about is that you can use within this framework different topographic indices to do this kind of discretization. So this HRU delineation approach therefore preserves the topological connectivity between upland and lowland areas, and this is the work that was done by Oruj Khan during his PhD. Here how it looks like after we identified those thresholds in the landscape based on distance from the river. Now we can break out the catchments to the series of these HRUs on landform elements, and then we decide, depending on our modeling approach, whether we want to do this distributed modeling approach where we obtain catchment properties for every pixel, or we may obtain catchment properties for every landform or HRU unit. This means that now we are only doing simulations across 4 pixels that they have different lengths, and these length units are coming from our topographic and geomorphic analysis. We may make further simplification and then aggregate the properties of these cross sections in the right bank, left bank, and headwater, and these delineate equivalent cross sections. Of course, if you are not in first order stream, we only have these right bank and left bank unit for model simulations. You can either perform simulations for a single subbasins or the entire catchment. Using parallel processing toolbox, we can do these simulations across multiple units and store the results. Here, how the results look like for these Stanley subbasins as part of the Hoori River catchment, where we have soil moisture observations. In the figure that I show on the top, I'm showing mean soil moisture from the subbasins that is simulated using the distributed pixel approach, and the purple line is the observations. And I should mention that here there is no calibration done, and we are using default hydraulic parameters that are obtained based on soil grids data sets for Australia. And then in the bottom figure, essentially, I'm comparing soil moisture simulations from all these different cross-section delineation approaches in a SMART. And as you can see, the lines are pretty close, and the reduction in accuracy by making these simplifications of these subbasins to equivalent cross-sections is quite small. When I move further to differences between ET simulations from the distributed approach versus these equivalent cross-sections approach, you will see that at a daily time step, the differences are less than 0.2 millimeters per day. And when I'm looking at total runoff from these cross sections, the difference is on the order of 10 to the negative 4 millimeters. Of course, this is just experimented for a couple of catchments, and we need to test this modeling approach in other sites with different topography and soil hydraulic properties to see whether the same order of accuracy can be obtained. How about reductions in computational time? Here I'm just comparing the number of horizontal grid cells for the distributed pixel approach for the Stanley subbasins, which there are 505 versus 3 equivalent cross sections, which is 45 grid cells only. And if you look at the computational time, we are reaching from 16 minutes to 2 minutes for 1 year of simulations, which is quite good. And here I'm just trying to show the soil moisture simulation using these three equivalent cross-section approaches, again, for the Stanley sub-basin. One thing that you need to know that you see these features that are soil moisture essentially uniform, because these are our hydrologic response unit that we assumed are uniform parts of the landscape. And now at the moment we are looking at disaggregation approaches to further discretize these to finer units, but in the form of the ESM scale, probably getting the means soil moisture simulations for the sub-basin should be sufficient. This work has been published recently in environmental modeling and software, and all the source code are available on GitHub if you want to test this approach, particularly if there are catchments that they have good observational data sets. So in summary, we developed an approach that to delineate hydrologic response units in a way that they are preserving hillslope hydrologic processes. We are aggregating a spatial variability of subbasins properties at the landform scales. Our simulation elements are either distributed cross-sections or equivalent cross-sections. Therefore, we can reduce computational time significantly. The SMART modeling framework is a modular framework for alternate delineations of HRUs. I have some other routines that we can break up these catchments in different ways that I haven't released yet, but is under preparations, and we have a detailed user manuals and data set that would be nice also for teaching activities in hydrologic modeling classes. And with this, I would like to thank all of you, and I will take if there are any questions. Thank you.
If you have any questions, please type into the chat box or raise your hand.
So Hoori, and if we think of it in the ESM framework, we have for example, 1 degree by 1 degree model box. Do you still need a sub-watersheds, or can you just go directly to the hill slopes, to your representative cross sections?
But the question is whether we can actually represent the equivalent cross sections this way. I mean, I haven't tried that yet, to see at the 1 grid scale how this, the way that I saw it, I thought perhaps we delineate to the sub-basins and then we aggregate the fluxes at the sub-basins level. But we can try it as well, yes, using those hydrologic response unit, the way that we delineate it for the entire catchments, instead of using the catchment as a unit, using the elevation within 1 grid cell, and then see how these essentially elevation here varies, and identify these types of thresholds. But the issue would be the boundary of the grid cell of the ESM may not overlap with where you are releasing water to the system. That would be an issue. That's why I thought maybe going towards the watershed approach, as Randy Koster had in his 2000 paper, might be more appropriate. But I totally agree with your comment.
Both talks, I think the wonderful thing about it starts from the rivers. The rivers are really the organizing principle, and you're looking at distance away from the rivers. And so I think that makes a lot of sense. And so can we bypass the watershed, because ESM see the watershed boundaries, they see big model grids, they see vertical fluxes. Can we bypass, these sub-watersheds and watersheds, those many levels, which are really arbitrary, until it hits the hill slope? I mentioned in my summary of last webinar, Dave Tarbolton's work in the 90s, and shows that break of this continuum of slopes really happens at the slope scale, at the hill slope scale. I mean, the slope area relationship. So that is really fundamental skill. Can we bypass all the, fractal middle ranges and go straight to the end of this high, the scale invariance? Go to the hill slopes, and from the hill slopes, look at what are those representative cross sections and within the model grid, not watersheds. Let's get rid of watersheds. What I'm saying. Is it possible?
Yeah, that's a good. My only concern is how much then we transfer the fluxes to the river network. If we get rid of the watersheds,
right,
as a basic unit to transfer the water, because within the one, I mean, we can add a routing component on top of the ESM grid cell, but how that exchange is happening, I'm not sure. And I'm also at the moment doing some tests to see that maybe we even don't need 3 equivalent cross sections in some areas. And if I'm just doing 1 equivalent cross section for a sub-basin would be enough. So we can, now that we have these tools, we can run some numerical, at least, experiments to see what are the differences at different scales.
And by the way, I want to tell the audience who are not at our first webinar that we try to write up a summary after each webinar. And if you would like to get on the email list, please send me an email. And so I will include you, and then you can put in your comments and contributions and suggestions, whatever, into that document. And I think there's a question and comment from Banyak. Can we unmute him?
Yep, we can.
Go ahead.
Yeah. Are you on?
His hand is raised, but
well, he did type in a question, so we can read it out loud as well. His question was, did you count unsaturated flow above the water level? Torrential flow in unsaturated zone could be significant for connectivity and lateral flow processes in the context.
Thank you for this question. So we are including only unsaturated flow processes in this framework. So we solved the 2D Richards equation. And then, of course, we at the moment, there is no groundwater flow processes connected to this. We just have the free drainage at the bottom of the cross section. But that's the next step. And we are thinking a similar approach that Pieter has taken, for example, coupling this with the HSP approach. In terms of preferential flow, not at the moment, but as I said, if there is a hydrologic model that can be simulated, preferential flow processes can be coupled to this framework. The main message that we want to convey is that the question is not the hydrology model, but the way that we discretize catchments for runoff partitioning. But for sure, these are important considerations that need to be incorporated.
And I also want to remind the group that we've got a lot of problems, right? We have all scales of heterogeneity in the subsurface, and we don't have a whole lot of data. And we have macropores, we have fractures, we have karst, we have absolutely no, observation-based characterization of subsurface heterogeneity. And everybody agrees those are major headaches for us going forward. But let's step back a little bit. This exercise is not trying to answer all hydrological questions, how to model, how to represent heterogeneity. Our goal here is really clear. And what is the something that we know that we can do? Something hydrologists know as common sense, like water goes downhill. Valleys are wetter than ridgetops. Sunny slopes are warmer and drier than shady slopes. These are what we've been calling the hydrologic common sense. They have not made their way into the Earth system model yet. So this is what Martin has been calling the low-hanging fruits. And so we have a lot of problems of our own. We're not going to be able to solve it now, maybe next 20, 30 years. But we have been studying hillslope hydrology for half a century. And we have some common sense, we have some intuition, and this is the level we're talking about. And so let's focus our discussion on really not our, problems that we are just throwing our hands up. We don't know subsurface heterogeneity, and it varies over 13, 14 orders of magnitude. And if we don't know that, if we don't capture macropores, we can't get a flux right. That is all true. We'll continue to do that research, right? But here is really how to carry something we know so well already. We understand that hills converge water, and we have a organized structured heterogeneity, which is the hill slope, which is the topography. And topography alone can explain a lot. Topography tells us a lot about the terrains, what's beneath land surface, how thick the soil is, and often the vegetation from ridgetop to valley is very different. So topography carries so much information. Are we able to pull that critical information out and put this common sense in the Earth system models? So we're not really trying to tackle all the problems. We're trying to provide some guidelines for Earth system modelers who are not trained hydrologists, who don't have luxury to walk the hills up and down and trace the streams, and who can carry what or borrow what we can synthesize, and then put those in those models and make a difference in hydrology, make a difference in evapotranspiration, photosynthesis, carbon, and nutrient cycles. And that's our goal. And so the question here and the next webinar as well focus on this question: how do we divide a global model grid into hydrologically meaningful units, and they are hydrologically meaningfully connected? And that is the question. Krista has a question.
We have a few before Krista, actually. Steve had a question. Steve Burgess, I will unmute you. Go ahead, Steve.
I'm unmuted?
Yep, you are unmuted.
I just made a comment there that I really appreciated seeing the residual plot of ET, I think it was, where you plot what's measured minus what's modeled. And if you look at the various plots that we see, we've been going away, sadly, for about 25 years from useful plotting. Plotting an observed over a modeled is really obfuscating what we need to do. We need to see a single time series, and then we need to see a second time series showing the difference so we can pick up the mistakes we're making. Just a plea. I've been at it for at least 50 years, but let's just keep trying at that. That'd be very, very much appreciated. Do you get that?
Thank you, Steve.
And last one's just coming in now.
And next question, Gasson. Did you account for aspect and slope position effects on radiation temperature for ET calculation? And I think Gasson next week, and Leho will be speaking, and he will really focus on the aspect part.
So I should mention that for each of these equivalent cross sections, when we have these hydrologic response unit, for each element we are defining a slope, vegetation type, and climate properties. So this is incorporated, this variability. The model that we are using uses PET as an input, so we are not solving the energy balance equation, but that can be an important aspect, you know, if we add another, for example, use a land surface model. But this model in particular uses PET, but heterogeneity of vegetation along these equivalent cross sections and the changes in a slope and changes in the length of each of these landforms are incorporated in the modeling framework.
I think Krista has similar questions. I'm going to unmute Krista. Go ahead, Krista.
Hi, this is Krista. Can you hear me?
Yes.
Great.
Hi, Krista.
Hi. Yeah, I think my question has been answered, and I think it's really important that as this moves forward, that it tries, you know, the framework needs to unify the water and energy balance representations in these large models. So I do think it's critical to think about how to reconcile the different dimensions that affect. I mean, ultimately, it comes down to the equations that you're solving and how those equations are affected by the landscape. So you might also even think about how you deal with momentum transport. So anyway, I think you've got, you know, I think from the water perspective, this framework seems to be, you know, make a lot of sense to me. And it is sort of a nice extension of some of the work Randy Koster did, you know, with the catchment model, where you look at the nature not only of the watershed, but, you know, he sort of has the same idea in catchment, where he has, he delineates by sort of saturated zones and intermediate zones between saturation and wilting point. So you sort of deal with the controls on the processes through the way that you delineate. So I think that's great, and thank you. My only other comment is that it would be especially useful, especially when you're going to larger scales, if you could test the pattern using data sets like remotely sensed soil moisture, snowpack, temperature, and evapotranspiration from thermal data, because ultimately, it's like Steve Burgess's comment, ultimately we need to understand how the model structures affect the representation of the state variables that we care about. Thank you.
Thank you, Krista. That was a very good comment, and I totally agree with you. At the moment, I'm developing this smart model for the Little Washita watershed, where we have a good network of soil moisture observations, and a colleague of mine at North Carolina University have provided us with downscaled soil moisture data from remotely sensed satellite products. So we are moving towards that direction to use more remotely sensed products to evaluate and validate these models. Also at a smaller scale, collaborating with Dave Goodrich's group to get you know, runoff data sets from these first order subbasins at Walnut Gulch data to see how the model works in different landscape. But for sure, more evaluation and validations are required. Thank you.
Okay, I think I lost connection for a moment. Sorry about that. Any more questions and comments? Okay, if we are, you're awfully quiet, folks, and we can do this. It's 4 o'clock. We can stay on if we need to. Liz has to go off to another meeting, and I'll stay on. And if nobody wants to talk anymore, and I will wait for you guys to all log off if we want to call it off. And as usual, as before, I will write up a summary and try to circulate it around. And if you would like to be part of the discussion, please send me an email. Let's give you my email, and we will be in touch. And then next week, we're going to continue this discussion. We'll have 2 speakers. I think it was Leho and John Volk. And hope you can come and attend, and then we'll keep in touch. Anyone wish to comment? And if you raise your hand, you know what? I'm going to unmute everybody, maybe, and then so. I have unmuted everybody. If you would like to speak up now, you can just speak up. Well, there's a lot of feedback. Maybe not a good idea. All right, that's not working. So anyone has anything to discuss? And if not, I can give you a quick update on what's going on at CLM right now. And as you, some of you know, we have a Justin Perquette, a postdoc, working at NCART right now and doing some of the preliminary tests of how CLM responds to hillslope hydrology. And we had a workshop last AGU at in San Francisco that Justin provided a little update on what he has done. Basically, he looked at 4 columns and then moving water from the upper column to the lower column and see how this CLM responds to it. And the grid mean ET is significantly improved. And so this is something that's going on, but going forward, we really need guidance from the community. How do we divide the grid into columns? How many columns, and how are the columns connected? So some of the questions that we try to answer at the webinar are really practical guidances for us to go forward, and not just us. Many large modeling, global modeling groups, modeling centers are struggling with the same kind of questions. And hydrologists have a lot to offer because this is what we do. So this is the set of seminars designed to answer these questions for those of you who missed my intro slides. And so if you're interested in being part of this, please send me an email, and I hope to hear from you, and then we'll be in touch, okay? And so I'm going to say goodbye since nobody is going to say anything. And we're just going to see you next week. next Friday at the same time. Okay, thank you.